Hello, higher chemistry pupils, and welcome to this lesson on controlling the rate. We're going to work through the three topics for this section, so collision theory, reaction pathways, and kinetic energy distribution. We'll start with collision theory. So firstly, we're going to look at why reaction rates need to be controlled in industrial processes. Then we'll look at calculations using the relationship between reaction time and rate and think about what units we need. I can use collision theory to explain the effects of the following on reaction rates. So we've got concentration, pressure, surface area, which is related to particle size, temperature, and collision geometry. Let's firstly think about the first point. So why reaction rates need to be controlled in industrial processes. When we're thinking about the chemical industry, it may be anything to do from the manufacture of pharmaceuticals right up to large-scale production of materials and fuels, okay? So from the micro scale right up to the macro scale. All chemists in all contexts are interested in maximising their profit because the chemical industry, like any industry, is run on wealth creation. It needs to make money, otherwise it can't continue to make product. So we've got to balance out, on one side, if rate is too low, then it won't be economically viable. Okay, that means it won't be able to survive. If you're not making enough quickly enough, then you're not going to be able to survive as an enterprise. However, if the rate is too high, then this incurs more risk. For example, risk of explosion if you're working in a factory or something, okay? So these are the sorts of considerations that chemists need to make when they are manufacturing a product. There are many more considerations to do with other aspects of chemistry that we're going to look at further on in this topic when we start 3B next week. But for now, we're just considering about the rate of the reaction. So it can't be too low, otherwise it won't make money, and it can't be too high, otherwise there'll be risk of explosion. So chemists have to find some sort of middle ground. Let's now think about the types of rate. So average rate was a type of rate that we learned about in National 5. An average rate is a change in quantity divided by the change in time. Okay, so that quantity could be mass, it could be volume, it could be concentration, anything that could be measured throughout the course of an experiment. And the time, it's going to be measured in either seconds, minutes, milliseconds. It depends on the scale of your reaction, the type of reaction that you're going to make, okay? And the rate, say if, for example, the mass was in grams and the time was in minutes, then the rate would be measured in grams per minute. Okay, grams divided by minutes, so G min minus 1. Relative rate is the reciprocal of time. Okay, so that means it's the inverse of it. It's 1 over it. So relative rate is 1 over the time. So that means that the time would be 1 over the rate. Okay, and it's going to be given the units, whatever the time is, to the minus 1. So seconds to the minus 1, minutes to the minus 1, and so on. Okay, because it's reciprocal. Relative rate is a new concept for hire, and it's one that we need to be familiar with. Average rate was from Nat 5, but we still need to be familiar with it because it sometimes crops up in various contexts throughout hire. The sort of data that you might get for average rate. So let's imagine you did an experiment with hydrochloric acid and marble chips, so calcium carbonate. Okay, and you were looking at the volume of gas, volume of carbon dioxide that's produced over a 50-second period. Well, you'd be measuring it for longer than that until this kind of time stopped. So the volume of gas stopped, and then you stop the time. But let's say we wanted to find out what was the average rate in the first 20 seconds. Okay, so that's from 0 seconds to 20 seconds. Okay, so that's 20 seconds. Well, 35 centimetres cubed of gas was released in that time. So 35 over 20 is 1.75, and the unit would be centimetres cubed per second. Oh, sorry, I've missed out the 5 there. There we go. 1.75 centimetre cubed per second. So that would be an example of average rate. And that is useful when we're looking at the course of a reaction and we want to find the rate at different points within the reaction, okay? Or it could be the whole course of the reaction and comparing it. Relative rate would be, for example, if you had like a clock reaction. So e.g. clock reaction, where you were looking at a reaction with an end point, okay? And let's imagine that we did this with an acid at different concentrations and we were measuring the time. You remember you've done this and you've got the X at the on the white paper or the white tile underneath the beaker, and you're measuring the time for it to disappear. And so at 1 mole per litre, it took 22 seconds. At 0.1, it took 210. So we can look at the relative rate. So at this concentration, the relative rate would be 1 over 22, which is 0.045, and that would be seconds to the minus 1. Okay? At this concentration, the relative rate would be 0.00476 seconds to the minus 1, and so on, because that I've just done 1 over 210 there, okay? So that's how we would calculate relative rate, 1 over the time. Relative rate graphs follow this sort of format, and if you were given a relative rate graph, you might be asked what was the time when the concentration was a certain way, okay? So, for example, when the concentration was 1, we find that we go up here and that corresponds to, if I just keep this up here, it should join up. That corresponds to when the rate was 0.4 seconds to the minus 1. So what was the time? Well, time is going to be 1 over 0.4, which is 2.5 seconds. Okay, so you would be expected to calculate time from rate and vice versa. All right, let's now think about the factors that affect the rate. So we've got particle size, pressure, concentration, temperature, and collision geometry. Let's consider each of these in turn. So particle size relates to the size of the reactant that is in solid form. Okay, so often we would talk about comparing lumps with powder. For example, if we were talking about, in this example, it's marble, which is calcium carbonate or chalk, okay? And we can see that when we've got the single particle, all of these surfaces will react with the acid. And in this one, only all of these ones, so many more surfaces are available to react, even though the number of atoms is exactly the same. So what we've done is we have kept, if I highlight the original surfaces, these are all the ones that were in the original particle, and that corresponds to all of these. That's kind of not right. There we go. These ones. And now we've got all these new surfaces that are also able to react because the particle size has been made smaller. So decreasing the particle size increases rate because the surface area of reactant has increased. So one thing to remember is that if we want to increase the rate, then we can decrease the particle size, which can also be phrased as increase the surface area. Okay? Next, we're going to just look at pressure, and I only want to show you this to demonstrate a concept because actually we're going to be looking at the chemistry of gases in more detail in the next section when we look at molar volume. But for now, I just want to give you a quick overview of what pressure is. We're talking about the same number of particles, so if we were to count these up, it's the same number as in here, but in this, if we call this A and this B, in B, they've got less space that they can take up, so the volume available is less. So same number, so pressure, changing the pressure means same number of particles in a different volume. Okay, so if we if we decrease the volume, there's less space for them to move around, so the pressure increases. Okay, hopefully that makes sense. The majority of the concepts that we've seen this in is though to do with concentration. With concentration, we've got a different number of particles in the same volume. Okay, so here we had different volume, same number of particles. Here we've got different number of particles, same volume. Okay, so let's, if we're doing the same example as before, so we've got hydrochloric acid and calcium carbonate. In this one, we've got them both as the lumps, okay? But here we've got 1 molar acid. That can also be written as 1 mole per litre, the capital M. And that's just mole per litre. But we can see in the 4 mole per litre, we've got way more, 4 times more acid particles. So that would be hydrogen ions and chloride ions available to react at the surfaces. Okay, so increasing the concentration increases the reaction rate because we've got many more particles available. Okay, just remembering these words, we actually learned these words in 1st and 2nd year, but it's just concentration is a measure of how much solute has dissolved in a particular solvent. Okay, so the solute would be the hydrogen chloride gas and the solvent would be water, and you make the hydrochloric acid solution. This might appear in this format. So we've got a graph here where we've got 2 lines, this dashed line here, which is the higher concentration, and this other line, which is the lower concentration. So both start off at the same initial point and then they both end up at the same final point. But the higher concentration happens faster. The reaction happens faster for the reasons that we've outlined. So the graph is steeper for the higher concentration, and the lower concentration, the graph is shallower. But you'll see the overall change is the same. It takes less times for the higher concentration, so it kind of reaches its full, it just kind of stops about here, okay? So that's how that might appear. For temperature, we have to come up with a new definition of temperature. So temperature is a measure of the average kinetic energy that all the reactant particles have. Okay, so you'll see here it's demonstrated with these sort of dots that represent the particles, could be the atom or ion or molecule, and an arrow to represent how fast it's going. So with a higher temperature, we've got like a longer arrow. Okay, but what we want to understand is that the size of this arrow is like the average size. Okay, so some of them will be smaller, some of them will be larger, but on average, this one here on the left is the low temperature where the particles are moving a bit slower than in this one here where they're moving a lot faster. They've got a lot more energy. Increasing the temperature means that all the particles are moving faster. They've got more kinetic energy. Therefore, there's increased likelihood that any collisions will be successful. Okay, so for the temperature, we're not actually increasing how many collisions there will be. We're increasing the likelihood of those collisions being successful. And that will become a bit more clear when we cover the middle section of today's revision, looking at activation energy. Okay. When we look at a graph showing this, we've got the shallower line of the lower temperature, and then we've got the steeper line for the, we've got the steeper line for the higher temperature up here, which is this dashed line, okay? So again, what we'll see is that for the higher temperature, the end point of the reaction is reached a lot quicker, so about here, whereas for the lower temperature, it's about here, okay? So it takes longer when we've got the lower temperature, faster when we've got the higher temperature, okay? A quick word about collision geometry then. So collision geometry is just a fancy way of saying what way are the atoms facing in the molecules, okay? And so say if we take this example of this bromine molecule, and it's approaching this propene molecule, to this carbon here. Now this carbon is not part of the double bond, it is not reactive. So if this bromine molecule hits the propene here, nothing is going to happen, okay? Whereas if we go over to this side and we look at this bromine molecule, if it hits the propene here, then because it's hitting the double bond, then it's got the potential to break that bond and add in. And in fact, what we would end up with is the molecule dibromopropane. Okay, so just like this, okay? So collision geometry is important because the atoms have to be facing the right way. They've got to be facing where they can add in, okay? So in summary, the successful collisions have to have correct collision geometry and sufficient energy. And the ways we can increase the likelihood of successful collisions are through the things we've discussed: concentration, pressure, temperature, and particle size. Let's move on to think about reaction pathways. So we can use potential energy diagrams to show the energy pathway for a reaction. I know that enthalpy change is the energy difference between reactants and products. So enthalpy change, remember, is what is written delta H. And I know the relative values for enthalpy changes for exothermic, which will be negative because energy is coming out, and endothermic, which will be positive because energy is coming in. I know the definition of activation energy, which we shorthand do EA, and activated complex. We're going to look at that in a wee second. And I can calculate the activation energy from potential energy diagrams. So if you're given a potential energy diagram like this, you can say, oh, there's how we calculate activation energy. We know the effect of catalysts and how catalysts work. Okay, so let's look at that. Firstly, for an exothermic reaction. So on the y-axis, we've got potential energy, that would be in kilojoules per mole. And then on the x-axis, we've got the path of the reaction. This is sort of an arbitrary way of showing time, okay? It's showing what's happening at the start of the reaction, what's happening at the end, i.e. like the journey of the reaction, okay? It doesn't have any units because it can't be measured in any sort of meaningful way, okay? So in an exothermic reaction, our reactants have a specific energy and our products have a specific energy. And something happens that will force the bonds in the reactants to break and then form in a different way, creating the products. Now, the height of that curve is going to depend on which bonds need to be broken. So it could be lots and lots of bonds that are very strong, or it could be not many and they're not that strong, okay? So the height is not what we're talking about right now. We're just talking about the difference between the reactants and the products. Now, because the energy has come down, this energy goes out, it leaves the reaction, and so the change in energy, delta H, or the enthalpy change, is negative. The opposite of this is an endothermic reaction. Again, the reactants have the set energy and then they follow a reaction pathway and end up with more energy as products. So the molecules formed in a different way. And because energy has had to come in to create the product, the delta H enthalpy change is positive. The activated complex is a concept that helps us to understand what is happening at the point between the reactants and the products, okay? So at some point between the reactants and the product, we are changing from one molecule to another molecule. And right up here, the maximum energy point, we've got this activated complex, okay? And what we're seeing here, if we just look at this for a wee second. So here's a similar example to what we saw before. The bromine molecule is approaching the ethene. And as this molecule is breaking and this bond is breaking, at the same time as this bond is forming, okay? So what we'll see is at some point, and it's kind of arbitrary to think about because it doesn't really exist like this. It's just a way of sort of understanding the transition between one set of molecules and another. But the bonds are kind of half formed and half broken. So this is what we're looking at here. Before the collision, we've got separate molecules about to collide. And then if they collide with enough energy, we can break this bond, and we can make this bond and this bond. And if that happens, then we get two new molecules at the end. So putting those different molecules onto the potential energy diagram, we can see that at the point of maximum collision, we've got the activated complex, that high energy state. The energy that's required to break the bonds in the reactants is called the activation energy, and it's the distance between the start and the highest point, okay? It will always be positive because it always requires energy to break bonds in a molecule. So that's the activated complex, and that is the activation energy. So this point here is the activated complex, and this difference between the numbers here is the activation energy. Okay, let's just sketch this out to show some numerical values then. So that one there is an exothermic reaction. So I'm just going to do an endothermic reaction. And let's say we've got 20, 40, 60, 80, 100, and 120. So the reactants start off at 40, they have to go up to 120, and then they come back down to 100 to form their products. That's the energy that the reaction has at any one moment. So to calculate the activation energy, we're looking at the difference between the start and the highest point, okay? So we're going up from 40 to 120, so that's 80. So that activation energy would be 80 kilojoules per mole, okay? Let's think about the effect of a catalyst then. So a catalyst works by providing a different route which allows the activation energy to be lowered. Okay, so if we look at the difference between this curve here, which is without a catalyst, and then the same reaction with a catalyst, the thing that's changed is the activation energy, okay? So this was uncatalyzed and then catalyzed, okay? Activation energy has been lowered, okay, because we've got this alternative route. What we'll notice is that whether we used the no catalyst route or the catalyst route, the distance between the reactants and the products is the same, so delta H would be the same in both cases, okay? The enthalpy change is not affected by the use of a catalyst. Let's now talk about kinetic energy distribution. Okay, so I know that temperature is a measure of the average kinetic energy of the particles in a substance. I can use Maxwell-Boltzmann distribution graphs to explain the effect of changing temperature on kinetic energy of particles and reaction rate. And I can explain the effect of temperature and adding a catalyst, and I've got a wee bonus of showing you concentration as well, in terms of the number of particles with energy greater than the activation energy. So this is what the Maxwell-Boltzmann distribution graph looks like. So we've already defined temperature as the average kinetic energy of all the particles in a reactant, okay? So it's the average, which means some of the particles are hardly moving at all, some of them are moving super fast, and most of them are somewhere in the middle. Every reaction will have the activation energy, which is the minimum energy required for the reaction to happen. And the only particles that will react are the ones that have a kinetic energy that's greater than or equal to the activation energy. So all these ones will. The ones in this area don't have enough energy to react. So what that means is when the particles, do this with the pen, when the particles want to react, so when they meet each other, they don't collide with enough force to break these bonds, okay? So what happens when we change the concentration of the reactants? Well, the activation energy doesn't change. Low concentration, high concentration, it's the same activation energy. But with the increased concentration, we've got more particles. Now we see the spread, the shape is the same. It's just its peak is higher in the middle. And at all points on this graph, it looks like roughly double. So we could say this probably represents a doubling of the concentration. So a doubling of the concentration is showing us roughly a doubling in rate. So we had these particles that were able to react at the low concentration, and we've got these extra ones that are able to react at the higher concentration. The effect of a temperature increase, though, actually changes the shape of the graph. So we'll see this is our initial curve. This is the lower temperature. When we increase the temperature, we'll see the maximum possible temperature has shifted to the right, okay? But there's still some particles that are hardly moving at all. The middle of the peak has moved over to the right, and it's slightly lower because we're talking about the same number of particles, okay? So the area under this curve should be equal to the area under this curve. What we'll see though is that we've got more particles, these ones here, that are able to react now because of the higher temperature. They've got more energy. So when we're at a higher temperature, many more collisions are successful because many more particles have a kinetic energy greater than or equal to the activation energy, i.e. they are moving fast enough to overcome the bonds in the reactant molecules. Finally, we'll talk about the effect of a catalyst. So here we're seeing the same Maxwell-Boltzmann distribution that we saw at the start, an uncatalyzed reaction. Activation energy is here and all of these particles can react. But the use of a catalyst reduces the activation energy. So now it's over here and all of these particles can react. So we can see the use of a catalyst vastly increases the reaction rate because we have so many more particles that can react, okay? So to increase the reaction rate in industry, chemists will often use a combination of these different techniques, using a catalyst, increasing the temperature, increasing concentration, decreasing particle size, and so on, okay? And they will look at whether a reaction is exothermic, endothermic, and we'll consider in some of the topics that are to come over the next couple of weeks some other techniques. But that's it for the controlling the rate section. I would recommend that you go through these same learning outcomes on page 2 in your booklet, check your understanding and let me know if you need any extra help. Okay, thanks everyone.